A few modules ago, we saw two very similar ionic compounds, lithium chloride and potassium chloride, both dissolve in water. One process was exothermic while the other process was endothermic. We know the thermicity depends on the bonds that break and the bonds that form. So let's think about those interactions in the solution process. We'll model the solution process as starting with the solute, shown here as the red and blue ovals, where the red and blue color represent areas of negative and positive charge, and the solvent, which in this case is shown by the water molecules. The solution can then be imagined like this, where the solute molecules are surrounded by solvent molecules. We can conceptually break this down into three distinct steps. Let's consider the solute first. If you look carefully at the solute, notice that the molecules are arranged to maximize the positive and negative interactions. While the molecules are touching one another in the solute, they are not in the solution. So they have effectively been separated from one another. The energy change that accompanies this process is called delta H solute. It will require energy to pull opposite charges. This is analogous to what happens when you break bonds. It is an endothermic process, and the sign of delta H solute is positive. Next, we need to consider what happens to the solvent. We need to make spaces inside the water for the solute molecules to reside in. These are sometimes called solvent cavities. In the picture, 4 of them have been formed to accommodate the 4 solute molecules. We know that in order to pull apart water molecules, we need to break dispersion, dipolar, and hydrogen bonding forces. The energy change that accompanies this process is called delta H solvent. It will require energy to break these forces. This again is analogous to what happens when you break bonds. It is an endothermic process, and the sign of delta H solvent is positive. Finally, we can consider what happens when the solute molecules go inside the solvent cavities. Our textbook calls this the mixing step. Notice how new interactions are formed between the solute molecules and the solvent molecules. Looking carefully at the picture, you'll see that the positive blue ends of the solute molecules are interacting with the oxygen ends of the water molecules, which are the negative ends. The negative red ends of the solute molecules are interacting with the positive hydrogen ends of water. The energy change that accompanies this process is called delta H mixing. With opposite charges interacting, the energy should go down, so delta H mixing should be negative, indicating an exothermic process. This 3-step process is simply a way for us to conceive of what is going on during the solution process. Of course, all 3 of these steps are happening at the same time, resulting in an overall enthalpy change for the process, delta H solution. Delta H of solution is then the sum of the 3 individual steps. We know that delta H solute and delta H solvent are endothermic and positive, while delta H mixing is exothermic and negative. So delta H for the overall solution process could be either positive or negative. This is somewhat like when we estimated delta H for reactions using bond energies, and the result depended on the relative strengths of the bonds that were broken and the bonds that were formed. Same here. It depends on the relative strengths of the intermolecular forces that are broken in the first 2 steps, and the intermolecular forces that are formed in the 3rd step. This means that the solution process can be exothermic or endothermic, and we cannot predict this ahead of time.